Welcome back to our mini course on Discrete Calculus with the Wolfram Language. I'm Alistair Forsyth, and this lesson is going over Introductory number theory. To start with, we'll have to define some of the language that we use here. Suppose x and y are two integers. We say x divides y if and only if y equals nx for some integer n. In other words, x divides y if and only if there exists an n that is an integer such that y is equal to n times x. We can check if any given x divides any given y using the Wolfram language, using the function divisible. Here we have y equals 10 and x equals 5, which will come back true because 10 is equal to 5n for n equals 2. A property of this function is that for any integers a, b, and c, if a divides b and a divides c, then a divides b plus c. If you're like me, this may seem a little bit unintuitive, but there's a really simple proof behind it. Take a divides b. That implies that there exists an integer n such that b is equal to na. Then, a divides c implies that there exists an integer m such that c is equal to ma. Combining both of these properties, we can write b plus c is equal to m plus n times a, which is just saying b plus c is equal to b plus c, or m times a plus n times a. From there, because m and n are integers themselves, we can say that m plus n is a new integer k, such that b plus c is equal to ka. Using this method, we've demonstrated that if a divides b and a divides c, then there must exist an integer k such that b plus c is equal to ka, so a divides b plus c. Another operator we use a lot in number theory is the modulo operator. In many forms of computing, there is a modulo operator which returns the remainder of division. In the Wolfram language, we have the mod function. Mod 12, 10 returns the remainder of 12 when divided by 10, or 2. In some other languages, this is written as x with a percentage sign y, which is read out loud as x mod y. Some applications of the modulo operator include converting time. Suppose you are given the time in a number of seconds and want to convert it into a sort of standard time output. To get the number of hours, you could take the total number of seconds divided by 60 squared, then take the floor operator of that. To get the number of minutes, you could take the floor operator of the total number of seconds divided by 60, and take that mod 60. That essentially gets you the remainder of the operation of getting the number of hours. For the remaining number of seconds, it's essentially the same thing. You take the total number of seconds, mod 60, which is essentially just giving yourself the remainder from that division for minutes. We can put this together as one chunk of code in the Wolfram language and see that if you're given 72,932 seconds, the time will come out to be 7 hours, 45 minutes, and 32 seconds. Another application of the modulo operator is a recursive definition of the GCD of a, b. Using the mod x, y function in the Wolfram language, we can write some code that will recursively call itself to find the greatest common denominator of two integers a and b. First, we have to assign our a and b values. Here I chose 420 and 860 because they're not easy to estimate the greatest common denominator for. Then, we repeatedly take r as the remainder of division, being equal to mod a, b, and then we reset a to be equal to b. If r is greater than 0, we set b equal to r, and if not, we print out a as our final answer. We do this once, and there's no output, so we go ahead and do it again. No output, so we go ahead and do it again. And now we have an answer, as 20. We can check this answer using the Wolfram language, just using GCD of 420, 860, which also comes out to be 20. Another form of operation we use in number theory is Congruence Mod K. In modular arithmetic, we say two integers, x and y, are congruent mod k if and only if k divides x minus y or k divides y minus x. There's a fairly simple proof that shows both of those definitions are actually equivalent, but we're not going to go into that today. A slightly more convenient explanation says x and y are congruent mod k if and only if there exists an integer n such that x is equal to y plus nk. And we typically write this with an equal sign with a third dash, and this is read out loud as x is congruent to y mod k. A notable rule is that if NA is congruent to NB mod k, and N and k are coprime, then A is congruent to B mod k. A congruence class or equivalence class is a collection of all integers that are congruent mod k for some specific k. For example, if you modeled a clock using equivalence classes of 12 hours, you could write one out as 1 a.m. day 1, 1 p.m. day 1, 1 a.m. day 2, and then so on and so forth until you got to 1 p.m. of day n. And we write out equivalence classes using brackets. So here we have bracket n bracket mod k, which would be the equivalence class of n in a environment mod k. Now, from everything you've learned today, you have the right tools to solve the clock problem. Now, this is just a simple word problem that I thought of one day and thought it was kind of cool. So, on a standard clock with an hour hand, minute hand, and second hand, does there exist a time at which the three hands split the face of a clock into 3 equal pieces? If you're like me, you might immediately think 12, 4, and 8, but if you think about it, that's not a real position on a clock, because for an accurate clock, the hour hand will move with each second. You can pause the video here if you're not ready for the solution, but we'll go over it right now. It actually isn't possible. Here's why. Let's suppose theta is the angle from the 12 on the clock to the hour hand. It then follows that the angle from the minute hand is 12 theta, and the angle of the second hand is 720 theta. Now all of these angles will be considered mod 2 pi because the angle from the 12 to the hour hand will reset when the hour hand passes 12 and completes a full rotation. So, if the problem is solvable, there must exist a theta such that 720 theta minus 12 theta is congruent to 12 theta minus theta, which is also congruent to theta minus 720 theta, which is also congruent to plus or minus 2 pi over 3 mod 2 pi. You should note that the plus or minus applies to all of these together, so if one is positive, the rest are, and if one is negative, the rest are. Using some math, we can simplify this to 708 theta is congruent to 11 theta, which is congruent to negative 719 theta, which is congruent to plus or minus 2 pi over 3, mod 2 pi. It then follows that 11 theta minus negative 719 theta is congruent to 730 theta, which is congruent to 0 mod 2 pi, as well as 708 theta minus 11 theta is congruent to 697 theta, which is congruent to 0 mod 2 pi. We can then see that the greatest common denominator of 730 theta, 697 theta, is equal to theta, which must be congruent to 0 mod 2 pi, following one of our rules from earlier. This retrieves the only value of theta that could be a solution. However, a solution where theta is 0 is not possible, as that would mean that all hands are in the same position. Therefore, there is no proper solution to this problem. Now, I'm undoubtedly not the first person to think of this problem, and I'm certainly not the first person to solve it in this manner. I just thought this proof was the most clear one that I could think of. And I thought the problem was, kind of a neat way to demonstrate all those bits of number theory. So, in this video, we went over modular arithmetic, the modulus operator, and some more tools for manipulating numbers and sequences. In the next 2 videos, we'll go over some more specific sequences, namely the Fibonacci sequence and prime numbers. For further details on this subject, you can check out the reference page for modular arithmetic on Wolfram Math World. And that's everything we have for today. I'm Alistair Forsyth, and thank you for watching. Bye-bye.